Good morning, everybody. Can you hear me?
Yes, sir. Good
Yes, sir.
morning.
Good morning, sir.
Okay, so this is a larger class, right? I mean, how many students are here now?
So there are 30 currently in the class.
30, okay. So, I mean, like in the honors paper, there was, I think, 19. But now
Yes,
it's more, right?
yes.
Okay. So some of you, for some of you, I have not met earlier. Like Prashant Kumar, I have not met. Okay. So who are the ones who were not there in the honors paper? Could you please just tell me your names?
Yes, sir. Prasant Kumar.
Okay. Next.
Paramita Banerjee, sir.
Okay. Kwashish Ghosh.
Sir, Monisha De.
Okay.
Sir,
Sir,
Upnisha Bhomik.
Okay.
Sir, Shoumi Mondal.
Okay.
Sir, Devjit.
Devjit Ghosh. Okay.
Sir,
Then?
Hassan Sahadi.
Okay. Hassan.
Sir, Shubhashish Ghosh.
Okay.
Sir, Arijit Mondal.
Okay.
Dipro Chakraborty.
Okay.
Shoham Adhikari.
Okay. Shoham Paul was there, right? In that honors paper?
Yes, sir.
Okay. Next. Anyone else?
Sir, Soham Kundu.
Shoham Kundu. Okay. Oyun Jana, is he in your class? Oyun Jana? Okay, so Oyun, I think we have not met earlier in the honors class, right? Oyun, can you hear me? Anyway, so let's begin, okay? And let me begin by sharing my screen. Can you see this slide?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, and is it changing?
Yes, sir.
Okay, fine. Okay, so let us begin. Now this course on satellite communication, this is actually kind of a, more application-oriented paper based on some of the principles of radio wave propagation that we had discussed in the last semester. That means assuming some of the basic principles of radio wave propagation to be correct, we will proceed further. And while in that earlier honors paper, we had mainly confined ourselves to understanding how radio signals could propagate over long distances using the ionized atmosphere as a kind of reflector of radio signals. In this course on satellite communication, the emphasis will be on trying to see how we could actually penetrate the ionized part of the atmosphere which surrounds the Earth and, kind of reach an artificial object in space which could handle some of our communication traffic. Okay. By traffic, we do not mean cars and vehicles, but in our parlance, traffic will essentially mean the flow of data or information from one point to another on the surface of the Earth. And we should keep this in mind that even in a country like India, long distance communication to a large extent is supported by or provided by satellites. Optical signals won't be able to travel such long distances. There have been some very isolated efforts at trying to put optical signals in place of radio signals, but that has not been a commercial success so far. So we have to depend on radio signals, at least for the foreseeable future. Just a minute, someone is trying, okay. So, when we talk about satellite communication or any kind of communication using the radio signals, then one of the first things, which is a kind of recapitulation maybe for those students who have earlier opted for the honors paper, is that the atmosphere which surrounds Earth is essentially opaque to different kinds of, electromagnetic signals. Now, if we look at this particular figure from left to right, say, then essentially what we can see over here is that this is a kind of electromagnetic spectrum where at the extreme left, just a minute, let me see if I could use the pointer. I think if I use the pointer, that will be better if I can design the pointer. Anyway, so what I want to say is that at the extreme left, you have the extremely small wavelengths of electromagnetic signals, which are typically known as the gamma rays. Then you have the X-rays, ultraviolet, moving on to optical, infrared. Then comes the radio frequencies or radio wavelengths. So in this entire atmosphere which surrounds the Earth, it is almost completely opaque, only allowing certain optical signals through a narrow optical window and radio signals through a much wider radio window to either enter or leave the atmosphere, okay, the surface of the Earth. That means any signal from an external source can either enter or leave only through this predefined radio window as well as the optical window. Now, because the optical window is much narrower in terms of wavelength, as we can see from this figure, the amount of or the scope of applications being developed using this optical window is much less. Okay, that also has put some kind of a that is also some kind of a discouragement for using optical signals for any kind of long distance communication. So whatever optical advances in optical signals has been made for application, they have been mostly limited to small distances between the transmitter and the receiver. But in case of radio signals, the distance is, practically speaking, limitless. That means we are sending signals, we are now able to send signals to satellites which are almost on the verge of leaving the solar system. That means that these satellites, which were launched some years ago, they are kind of moving out of the solar system because they are some kind of a deep space mission. But still, we are able to communicate with those satellites. That is essential, that we should be able to communicate with those satellites using radio signals and also receiving back the response from them. Communication is complete only when you have a two-way flow of information, right? That means only when you transmit a signal and receive a response as well. That is communication. So what we can see over here is that the radio window, it extends from roughly about 10 to the power, roughly extends from about, in terms of wavelength, 10 to the power minus 2 to about 10 to the power plus 2 meters. Okay, so that is like 1 centimeter to about 100 meters, right? So what we can see over here is that the radio window offers a much broader scope of applications being developed. Now, can any one of you quickly tell me what will be the frequency corresponding to this lower limit, 1 centimeter wavelength of radio window? The frequency. Someone quickly calculate and let me know and tell me what will be the frequency corresponding to this lower limit of the radio window.
Sir, it is about 3 into 10 to the power 10 hertz.
3 into
10 to the power 10
what's the unit?
hertz.
30 gigahertz.
30 gigahertz. Prashant Kumar, can you please tell me whether it is correct or not, this value?
Sir, about
Prashant Kumar?
Sir, I am calculating.
Yeah, please.
So,
Calculate and tell me.
Sir, it's about 30 gigahertz.
30 gigahertz.
Yes, sir.
So how many megahertz is that? If I want to express that in megahertz?
Sir, we have to multiply it into 10 to the power 3. It means 3000 megahertz.
3000
Yes, sir.
or 30,000?
30,000. 30,000.
Okay, sorry, sir. 30,000. We
30,000.
have to put 10 to the power 3.
Okay. So now, in this class, as I was telling you, that what we plan to do is that in the radio wave propagation class course, we had mainly concentrated that if this is a transmitter on the surface of the earth and that is a receiver, then we were trying to transmit a signal, get it reflected from some height, from some point, so that it could be received at the receiver. Now, naturally, one very logical question comes to the mind is that if the distance between the transmitter and the receiver was smaller, that means if the transmitter and the receiver were radio visible to each other, radio visible, optically they may not be visible, but if they were visible to each other through radio signals, then we could establish a direct radio link as well between the transmitter and the receiver, instead of going for this kind of a reflected echo signal, because as we know that the amplitude or the strength of the reflected echo is small, I mean it's less, it becomes a weak signal because the power associated decreases as 1 by distance to the power 4. Okay. So in this class today, what we plan to do is that we will try to understand how we can actually penetrate this ionized atmosphere and reach an artificial satellite in space, an artificial object, and that object will then once again do some processing and forward that signal to the desired receiver. Now it is important to understand that radio signals or use of radio signals for this kind of application, this has been mainly a fallout, or this has mainly come into existence after the Second World War, mainly when the Germans used these radio signals to great extent, very successfully, and it was but at that time in the late 1930s, early 1940s, we know that there was no such thing as an artificial satellite. In those days, by satellite, people used to mean the natural satellites, like the stars in the sky, some of the planets. So the concept of artificial satellites was not there at that time. But interestingly, one British science fiction author, Arthur C. Clarke, he wrote a book, 2001: A Space Odyssey, which has also been made into a very successful commercial film. And it was in this book that he first put forward the idea that if we could place 3 artificial objects in space, separated from each other more or less by 120 degrees from each other, that means this angle is 120, that angle is 120, this one is also 120, say. So under that kind of a situation, it may be possible to provide total global coverage with some areas having overlap. Okay. It was he who also first, kind of applied Kepler's laws. I think we are familiar with Kepler's laws of motion from our secondary or high secondary classes. So Arthur Clarke, he put forward that idea that if we put a satellite in an orbit around the equator, Earth's equator, geographical equator, if the orbit is circular and if it has a radius of about close to 42,000 kilometers, 42,000 kilometers not from the surface of the Earth but from the center of the Earth. So if you subtract the radius of the Earth from this value, you will get that what will be the orbital height or height of those artificial satellites above the surface of the Earth, so that they will have an angular velocity which will be the same as that of Earth. So anyone tell me, can you tell me the value of radius of Earth?
Sir, 6,400 kilometers.
6,400 kilometers. Is this Prashant?
Yes, sir.
Okay. So this is about 6,400 kilometers, roughly. So if you have an artificial object in a orbit, which is having a radius of 42,242 kilometers, if you subtract the radius of the Earth, then that will give you something like 35,800 kilometers. So these artificial objects, if they are put at that height from the surface of the Earth, then their angular velocity will be the same as that of Earth. In fact, we had earlier in our secondary or high secondary classes done that calculation, that if we match the centrifugal force and the centripetal force like that between a massive body and a less massive object which is around that more massive body, then the gravitational force of attraction is counteracted by the centrifugal force. And so we get an equation which is something like Gmm by r square equal to mv square by r, where capital G was, the universal gravitational constant. And instead of that r, we used to put r plus h, where the r was the radius of the Earth and h was the height above the surface of the Earth. So from there we could calculate that what will be the angular velocity or what will be the height of that object above the surface of the Earth, so that its velocity will be the same as that of Earth, the angular velocity. Now, why do we try to achieve that condition? I mean, what advantage does it give us if we can locate an artificial object in space which is having the same angular velocity as that of Earth? The important advantage of that kind of a setting will be that that particular object will be rotating with the same or moving with the same angular velocity as Earth. So that means it will always be visible above a certain point. That means it is not that this particular satellite or artificial object will be there for some time and then it will move away to any one of the sides. Not like that. It will be there for all times to come. That means 24/7, this particular satellite will be visible from some locations here. That particular satellite will be visible from some locations there, and this one from some locations there. Okay. So that means we, as an user on the surface of the Earth, we do not have to change our receiving system or transmitting system as well as the antenna to point towards different objects. Sometimes that object could be here, sometimes that object could be there or there. So that means if we put these objects at such heights that they are practically moving with the same angular velocity as that of Earth, then of course we have a much easier time for transmission and reception of signals, because once I fix the antenna towards one of these directions, that direction is going to remain fixed. So as we can see that Arthur Clarke, as you know, is he was a science fiction author. Okay. And as is expected from a science fiction author, they have ideas which are well ahead of their times. So when he first put forward this idea around 1942 to 1945, around that period of time, artificial satellites were not at all there. Even humans have not started, kind of any exercise to develop that kind of a capability. So now, the importance of this kind of a condition where you can put these artificial objects in space in such a way that they will be moving with the same angular velocity as that of Earth. That is the criteria which is satisfied, which is necessary for the communication satellites. So majority of communication satellites are in geostationary orbit. These orbits are known as geostationary because here the satellites are kind of stationary with respect to Earth. So these are some of the conditions which are necessary. One of the conditions, I should say, is that in order to qualify as a geostationary communication satellite, these objects have to have an altitude of roughly about 35,786 kilometers, and the typical path length from an Earth station, that means the transmitting and receiving station on the surface of the Earth, that typical path length will be about 38,500 kilometers. Now, one of the important points to consider here is that because these signals are traversing such a long distance, one way, this is the one-way distance. That means from the transmitter to the satellite, it's something like 38,500 kilometers. Then again, from the satellite to the receiver, it may be something like that. So basically, the signals which will be received by the geostationary satellite, they are extremely weak because, as I was mentioning, that the signal power varies inversely with the square of the distance traversed. Similarly, the signals that will be received back at the receiving station, at the receiver, they will also be extremely weak. So the usual sequence of steps which have to be followed on board a communication satellite is, first of all, you should receive the signal, then there should be an amplification of the signal, finally there will be a retransmission of the signal. That means first of all you have to receive the weak signal, and because they are weak you have to perform some amplification on the signal, and then you have to retransmit that signal to the desired user. So what we can understand is that because of these kind of sequential processes which have to be followed, so there are very stringent requirement for discrimination of the uplink and the downlink signals. That means there should be a clear difference between the uplink signal, which is from the Earth station, the satellite, from the downlink signal, which is from the satellite to the Earth station. But we have to be careful that the hardware that we put on board the satellites, that is also that should also be of major consideration. Okay, that is because of the fact that the cost of designing, launching, and finally placing a geostationary satellite in orbit is extremely high. Okay, like 1 kg of matter, if you want to put 1 kg of any object in geostationary orbit, that will cost more than 25,000 US dollars, just 1 kg. So you can understand that that has put a limitation on the weight of the satellites. That means we cannot go on making satellites bigger and bigger and putting in more and more hardware into it. And that is why present day, you must have read that we are gradually going for larger number of smaller satellites. These satellites are referred to as CubeSats or nanosats also, nanosatellites. And if we put more and more hardware, electronics inside a satellite, then there is also a limitation of electrical power which is available on board the satellite once you have placed the satellite in orbit. That is, once a satellite is placed in orbit, we can understand from common sense that the only source of energy, natural source of energy available is the incoming or the incident solar radiation. So the incident solar radiation, that has to be harnessed on board the satellites and converted into some kind of electrical power. But there also we have limitations. That is, even with the tremendous advancement that we have made, the conversion efficiency of solar cells are extremely poor. Okay, that means solar cells, they convert the incoming solar radiation into electrical energy. So that efficiency is only about 15 to 17% at the beginning of their lifetime. That means for a brand new solar cell, that's the kind of conversion efficiency that you can expect. And with the gradual passing of time, with the gradual aging of the solar cells, their conversion efficiency further decreases. So that means we are beginning with a system which is kind of wasting more than 80% of the incident solar radiation. And that wastage gradually increases and may become 90 to 95% after some years. So, because once you put a communication satellite in orbit, you expect it to perform for at least 8 to 10 years. Okay. Only then, you have some kind of a revenue generation from that. Before that time, it is only like kind of trying to get a stage of break even. That means the amount of money that you have put in to the development and launching of that satellite, that has to be recovered. And only after some years, the manufacturer can think of getting some profit out of that satellite. So they also have to keep this in mind that they cannot put too much of hardware into the satellite because that will further increase the cost of launching. And at the same time, they have to be very careful about the electrical power requirement because the solar cells are very poor converter of energy. Okay. So, the high cost of these satellite design, their launching cost, and also the station keeping. Okay, this is something like a term used as in the, like housekeeping, which is used in the hospitality industry to indicate, to mean that like, they clean the linen that is used in the hotels and things like that. So just like that, in case of your satellite also, once you launch a satellite, you have to go on monitoring the various subsystems through some of the parameters which are transmitted by the satellite. It is not that a satellite, once you launch it, it will perform completely independently without any kind of intervention. It is not like that. These satellites, every satellite needs monitoring, and that process has to be done through sometimes a network of ground control stations. So the communication capacity of the satellite, it should be kind of optimized, because if we want to increase the or maximize the communication capacity, it may so happen that we end up making the satellite too heavy. So that will once again push up the cost of launching the satellite and putting that in successfully in the geostationary orbit. So it should be something so that the manufacturer could recover the costs within an operational lifetime. It may not be 10 to 15 years. I think 10 to 15 years is being highly optimistic. Typically, the lifetime is something, I mean, the recovery time, the recovery cost, that is about 7 to 8 years, typically. Another important thing is that once you have launched the satellite, the signals that you receive, because we had already mentioned that the one-way distance from an Earth station to a geostationary satellite is something like 38,000 kilometers plus. So the signals that will be received back from the satellites at an Earth station, that will also be extremely weak. Like, it may be of the order of 10 to the power minus 8 to 10 to the power minus 10 watt. And no electronic circuitry will work at that level of power. So at the receiving station, the first thing that is needed is we have to use we have to boost up the received signal using some large aperture receiving antennas. And some of these receiving antennas could have diameters even up to 30 meters, which is like 100 feet. Although presently, the technology has changed, and we could also work with signals, weak signals, using antennas which may be, kind of size of our palm of our hand. Okay, the palm of our hand, something like that. And some of the satellites nowadays, instead of being extremely big ones, as was the tradition in the early days of satellite launch, we are now working with satellites in orbit which may be, a few kgs. Okay. Correspondingly, their power requirement is less, and the antenna, earth station antenna requirement has also come down. So as I was mentioning that although classically geostationary satellites are still the most preferred form of artificial satellites used for, satellite communication, but there has been, over the last, say, 20 years or so, efforts and initiatives to also use other categories of satellites which are not geostationary for the purpose of communication. So let us see if these videos, if they work or not, where we can have some idea about a constellation of satellites by the name of Iridium. Okay, Iridium. Let's see if it works or not. So that was about, one of the one of the new constellations, Iridium, as I mentioned. Were you able to watch the video?
Sir, we were able to watch, but the sound was not. We weren't able to hear anything.
You weren't able to hear the sound, right? Anyway,
No,
I
sir.
will share that YouTube link. Yes, I will share that YouTube link with you so that you can watch it on your own system. Okay, so moving ahead.
Hello, sir.
Yes.
Sir, I have to leave the class for my mother's vaccination.
Okay. Okay, fine.
Sir, what about my attendance?
Okay, let's see. You have attended one period, right? So you will get that.
Yes, sir. থ্যাংক ইউ স্যার। আমি
Okay.
মেসেজের রোলটা লিখে দিয়েছি।
Okay, fine.
ওকে স্যার, থ্যাংক ইউ স্যার।
Welcome. So, as I was telling you that, can you see the screen, everybody?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So, as I was mentioning that when Arthur Clarke had, first postulated that idea that we could put artificial objects in space, he did not name them satellites, because at that time the term satellites was mostly used for natural objects like the stars and the planets. Instead, he used the term extraterrestrial relay. Okay, as you can see from here, extraterrestrial relay. So what happened was that was still oh, just a minute, sorry. Hello. Well. Oh, अच्छा. মানে হিট সিঙ্ক কিছু নেই না ওরকম? হুম হুম ও আচ্ছা আচ্ছা Mm-hmm. তাই দেখো। ও হুম হুম আচ্ছা, তাহলে দেখো ওইভাবেই যদি প্রিফার বেস্ট কিছু করো। হুম 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 ঠিক আছে, দেখো তুমি এই উইকে যদি রেডি করতে পারো। হুম না, অন্যটা ওই যেটার অবস্থা খারাপ। না, অন্যটা নয়, মানে এইটাই কথা বলছি। হুম আচ্ছা 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 হুম 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 আমি তোমাকে কিছুক্ষণ বাদে তাহলে ফোন করছি, হ্যাঁ? আচ্ছা আচ্ছা Okay, so as I was mentioning that he called those objects in space as extraterrestrial relay, and by extraterrestrial relay he meant essentially some kind of an intermediate point in space where the transmitted signal is first received, then that sequence of amplification and retransmission is done before it is received by the receiver or the receiving earth station. So all these ideas that he had put forward in 1945, sorry, uh, the first successful launch of satellite was still about 12 years later. Okay, and it was Sputnik 1, we know, which was launched by the then USSR on 4th October. So it was kind of a low Earth orbit, that means a few hundreds of kilometers above the surface of the Earth. So that was the orbital altitude of Sputnik 1. And secondly, immediately afterwards, the United States, they also became extremely active and tried to develop a kind of a similar kind of artificial satellite of their own, and they named its code Signal Communicating by Orbiting Relay Equipment. So this was designed by the US Air Force, and It was on 18th December 1958, about 1 year after Sputnik 1, that SCORE was put into a low elliptical orbit with a period of about close to 100 minutes. And it operated with at frequencies of about 150 megahertz for uplink and about 132 megahertz for downlink. But because it was kind of a very hastily designed satellite, so the design was not good. So its batteries failed only after 35 days in orbit. So SCORE lasted for just about 1 month or so in orbit. Thereafter, the first communication satellite, which became, in which, the common people also came to know about all these things, was named ECO-1 and ECO-2, which were launched by AT&T, the company, in August 1960 and then in January 1964. So these were basically like some kind of, orbiting balloons of about 100 feet diameter, 100 feet diameter in space. So that's a big one. Okay. And they essentially served as passive reflectors. That means because they were orbiting balloons, which served only as passive reflectors, so they did not have any kind of, onboard processing capability. That means they could not, kind of amplify and retransmit the signal. They could only redirect the incoming signal. Okay, they were passive. When you have some kind of amplification and retransmission capability on board a satellite, so that is some kind of an active system. Okay, so they were also put into some kind of low Earth orbit with orbital period of about 118 minutes or so. Okay. Now, the first successful, geosynchronous communication satellite was launched in 1963. That was named as the SYNCOM. Okay, SYNCOM. So that was in 1963, SYNCOM 2, which became successful, and SYNCOM 3 was in July 1964. And then the first commercial geosynchronous satellite was Intelsat 1, okay, which was developed by the Communication Satellite Corporation. That was launched on April 6, 1965. The birthday of commercial satellite communication, that is usually taken as 28 June 1965, the day when, routine operations began between the United States and Europe. Now, while all this was happening globally, India, we had also realized that better communication is extremely important for the development of the country. And it was Dr. Vikram Sarabhai, the founder of the Indian space program, who took the lead in the 1960s. But you should also be aware of the fact that long before Dr. Vikram Sarabhai, the founder of our department, late Professor Shishir Kumar Mitra, after whom the departmental building is named as Shishir Mitra Bhavan. So he had started this kind of experimental radio wave propagation in the 1920s and 1930s. And thereafter, he was also active in indigenous development of ionospheric sounding systems or high power transmitters. So, as I was mentioning, Professor Shishir Kumar Mitra, he assembled the first, kind of manual sounding system in Asia. This was a kind of a high power transmitter and receiver. We have read some of it in our radio wave propagation class. And he installed it at our field station of the university, which is located close to Horinghata, the dairy farm of Horinghata, just right next to Bidhan Chandra Krishi Vishwavidyalaya. So that was the first time in Asia that that kind of a system was being developed. And we can find details about our field station in our departmental website. Of course, this website is now undergoing some changes, I learned. And then there were several other efforts also, like the Committee on Space Research of the United Nations that was set up in 1962. And then India also set up the Thumba Equatorial Rocket Launching Station with support from USSR, USA, and France. It was around this time in 1966. So remember that in 1965, the first commercial satellite communication was established. And it was in 1966 that our department also started receiving signals from different kinds of satellites using receivers located at the field station. So at that time, the satellites which were tracked were this Explorer 22 and Explorer 27. They were low Earth orbiting satellites which operated at frequencies of about 40 and 41 megahertz. Then in 1972, the Space Commission was established by the Government of India, which later on became the Indian Space Research Organization as we know it today. Now, ISRO has several, centers, and our department has a long, tradition of working with ISRO. There are several instruments which are operational in our department and also at the field station in collaboration with ISRO. So this Vikram Sarabhai Space Center is one of the premier laboratories of ISRO located at Trivandrum. Then there is also an ISRO Satellite Center and Sriharikota, from where the launching of Indian satellites takes place. The Space Application Center is located in Ahmedabad. In addition, there is also a physical research laboratory, National Remote Sensing Center, as well as the National Atmospheric and Research Laboratory. Then in 2003, our university has also established a center in memory of late Professor Shishir Mitra. So these are just some of the early space-based programs which were undertaken by India. Before going into the details of this particular course, we should also be familiar with at least the background of the subject. Okay. It is not that, we should go into learning a particular course without knowing where we stand. Okay. So there have been several, programs like the INSAT. Then India also has a Goggle network, which uses GPS for navigation. And our department also operates, a number of these satellite signal receiving systems. Now, coming to the motion of the satellites, their motion are mostly governed by the Kepler's laws of motion, Kepler's planetary motion laws. So, there are three laws. Firstly, that the orbit of the smaller body around the larger body is always an ellipse, with the center of mass of the larger body being at one of the two foci, and the orbit of the smaller body, it sweeps out equal areas in equal time. But the one with which we are more interested is that it also tells us how to calculate the time period of the satellite around Earth. That follows from the third law of Kepler. That is, the square of the period of revolution of the smaller body around the larger body is equal to a constant multiplied by the third power of the semi-major axis of the ellipse, orbital ellipse. So here you can see that it is t square equal to 4 pi square a cube by mu, where capital T is the orbital period, a is the semi-major axis of the orbital ellipse, and mu is the Kepler's constant. Okay. So, what we can understand is that this mu, this is actually the product of the universal gravitational constant. Mu, as we had defined here, it is the Kepler's constant. So that Kepler's constant is equal to the product of the universal gravitational constant capital G and mass of the Earth. And this Kepler's constant has the value of about 3.986 into 10 to the power 5 kilometer cube per second square. And we already know that the universal gravitational constant is, this G equal to 6.67 10 to the power minus 11 Newton meter square per kg square. Okay. So following this, we can actually be able to understand and calculate the orbital parameters of the different categories of satellites. So satellites are usually classified according to their orbital altitudes, like the low Earth orbiting satellite, which is also known as LEO. It is at altitudes of about 800 to 1,000 kilometers. So because it is around 800 to 1,000 kilometers, so there will be a number of times each day that satellite will rotate around Earth. So there will be more than one pass of the satellite, but because the orbital altitude is like 800 to 1,000 kilometers, their velocities will be high. Okay. So when their velocities are high, then each of these passes, by a pass, what is meant is that just like the sun, the moon, or any star, a low Earth orbiting satellite will rise from one of the horizon, reach a certain point in sky which is high above the user, and then set at the other horizon. If an object is below the horizon of the user, then of course the user cannot see that object or receive any signal from that. So that pass typically lasts for about 7 to 12 minutes in case of a low Earth orbiting satellite. Now, having noted the value of the orbital altitude of the low Earth orbiting satellites, could you quickly calculate what will be the orbital period of this kind of a satellite? Orbital period of a low Earth orbiting satellite and its corresponding orbital velocity. These are the two important parameters. You please calculate You know that what is the value of the orbital altitude? It is like say 800 to 1000 kilometers. So you can take the value of 1000 kilometer for the ease of calculation. But you have to keep this in mind that the value of this A over here, the value of this A, this will be like the addition of the orbital altitude plus the radius of the Earth. And the value of mu that you have already that we have already seen over here, that the value of mu is nothing but 3.986 into 10 to the power 5 kilometer cube per second square. So with this knowledge, just calculate and tell me what will be the value of orbital period of a low Earth orbiting satellite. So please calculate and tell me the value.
Sir, around 1.8 hours.
1.8. 0.8 of an hour means, could you please tell me in terms of hour and minute?
Sir, 105 minutes I'm getting, or 1 hour 45
About
minutes.
1 hour 45 minutes. Okay. Anyone else?
Sir, 1 hour 48 minutes approximately.
And what's the corresponding orbital velocity?
Sir, 7.33 kilometers per second.
7 point?
33 or 34.
Sir, nearly 26,000 kilometer per hour.
26,000 kilometers per hour.
Yes,
Could you
yes,
please
sir.
tell
Fine.
me in terms of kilometer per second?
Okay, sir.
So 7.34.
Yes, sir. Around 7.2, 7.3 kilometer per second.
Okay. Pratyush, have you done the calculation? Pratyush Kant?
Hello, sir.
Yes, have you done the calculation?
No, sir, I am calculating velocity. So time period was 1 hour 45 minutes.
Okay. Okay, so the value of these will be what some of you have already obtained, that it's like about 7 kilometer per second. That's the orbital velocity. So what it means is that in a time period of over a time interval of 7 to 12 minutes, it will be covering a distance of roughly about how much? 7 into 60 into 7. So that will be something like 7 kilometer, that into 60 per minute into
Sir,
say
about
7 minutes.
3,000.
It will be like 60 into 49, so close to about 3,000 kilometer, right? Minimum.
Yes.
So what we can understand is that the signal that we will be receiving from that kind of a satellite, a low Earth orbiting satellite, that will have a huge amount of spatial variation. Okay. In contrast, the time change or the temporal variation will be relatively less, almost insignificant, because in 7 to 10 minutes, the atmospheric parameters under normal condition do not change drastically. But over a space of like 3,000 kilometers, okay, that this particular satellite signal will be traversing when it is in view from one point. So over this arc of 3,000 kilometers, the atmospheric parameters will be changing by a lot. Like for example, 3,000 kilometer means that you are tracking suppose from Kolkata, you are tracking one low Earth orbiting satellite, and it is moving from some location, say over Trivandrum, and going beyond Kolkata to at least, like Jammu and Kashmir, something like that. Okay. So over this entire span, it is transmitting signals and you are receiving that signal. till it sets below your horizon. So the spatial variation of the atmospheric parameters will be quite high in this kind of a satellite signal. In contrast, the temporal variation is almost insignificant. And what we can write is that essentially for this kind of a satellite, the variation of the signal is primarily a function of space. Okay. Going to the other extreme, where you have the geosynchronous satellites. Now, there is also, we have used two terms. We had sometimes earlier, we had mentioned geostationary, and now we are saying geosynchronous. In some of the textbooks, you will find that it is written as if they are one and the same, but it's not so. There is a difference between them, between geosynchronous and geostationary. We will come to that later. I think I will stop here today and continue with it in the next class. The next class, I think, is on Wednesday, right? Wednesday 9 to 10, right?
Sir, actually, we haven't still received the schedule for our classes.
Oh, okay. I will tell your coordinator is, I think, Dr. Pulak Mondol, PM.
Yes.
So I will tell him to share that with you.
Okay.
Did you have any class last week or what?
No, sir. This is our first class.
Oh, it's your first class. Okay. So I think my classes are on. The next one is on Wednesday. Okay. Anyhow, I will tell him to share the routine with all of you. Okay. Okay. Now, please give me your attendance. That means please tell your class roll number sequentially. Okay.
C301.
Yes, tell me your class roll number sequentially.
Sir Devjit Ghosh, EC301.
Okay. Next.
Sir Shubhadeep Mukherjee, sir 303.
Okay. Then.
Sir 305, Mousumi Shao.
Okay.
Sir 306, Monisha De.
Okay.
Sir Shoptorshi Ganguly, EC308.
Okay.
Sir Shoumi Mondal 309.
Okay.
Sir Sheikh Mohammed Safiq Anwar 311.
Okay. Next. Who is next? Hello.
Sir 3015, Mousumi Mondal.
Sir 314,
315, right?
Yes, sir. Mousumi Mondal.
Sir 314, Stromona Majumdar.
Please tell me sequentially. Then next. Okay. Then
Sir, Shantan Majumdar 319.
Sir, Devangana Boshak 320.
Sir, Ognisha Bhaumik, my roll number is 321.
okay.
Sir, 322.
Next.
So 323, Subhashish Ghosh.
Sir, Shiny Roy 401.
Okay.
Sir,
Then next.
405 Sheikh Mahamadul Hassan Sahadi.
405.
Yes, sir.
Okay.
So 407 Arijit Mondol.
Okay.
408 Shoham Pal.
408.
Yes, sir.
Okay.
411 Shagnik Nayak.
Next.
Sir, 420 Chirantan Ganguly.
Then.
Sir, 422 Amit Chakshar Sanyal.
Okay.
423 Dipro Chakraborty.
Okay. Next. Who is next? After
Sir,
423.
I guess Soham Kundu is trying to give his roll attendance 424, but his mic is not
424
working.
Soham Kundu, sir.
Okay. Next.
Sir, 433 Pratyush Khan.
Okay. Next.
Sir, 438 Prasant Kumar.
Okay.
Sir, 441 Suprabhat Bhattacharya.
Sir, 439 Ritik Majumdar.
Sir, 440 Shoham Adhikari.
আমায় sequentially বলো।
Sir, first 439 Ritik Majumdar.
439, 440, 441. তারপর anyone else?
Sir,
432.
432.
32.
Why didn't you give your attendance earlier? Can't you follow what I'm saying?
Sir, network lacking.
Next.
Ravi Kumar Thakur, sir. Roll number not provided.
Okay. Anyone else?
Sir, roll number 313 is also present. I think her mic is not working.
313.
Yes, sir.
Okay. Okay, 302. Okay. So now I have 33 roll numbers. Are you 33 in number?
So the total student strength is 46.
Okay. So anyone else left now?
No, sir. I guess everyone who was present has given their attendance.
Okay, okay. Okay, thank you. So the
Sir?
next class will be on Wednesday, 9 o'clock.
Sir, which book can we follow for this topic?
I will tell you in the next class.
Okay, sir.